Have you ever wondered how your computer protects its memory and manages multiple tasks at once? Welcome to the fascinating world of protected mode, a mode of operation within the x86 processors. It's like an unsung hero that works behind the scenes to provide some pretty crucial features like memory protection, multitasking, and enhanced system stability. Contrasting with the simpler real mode, protected mode is a vital part of the x86 architecture, and it's commonly used in modern operating systems. So, whether you're typing up a report, streaming your favorite show, or running a complex coding project, you've got protected mode to thank for a smooth and secure computing experience. As we delve deeper into the workings of protected mode, we'll uncover how it facilitates memory protection, address translation, multitasking, privilege levels, and so much more. So buckle up for an exciting journey. Let's delve into the key features of protected mode, starting with memory protection. The first pillar of protected mode is memory protection. This indispensable feature allows for the use of virtual memory, enabling each process to have its own unique, isolated address space. But why is this important? Well, imagine you have multiple processes running on your system, each with their own set of data and instructions. If one process could freely access the memory of another, it could potentially corrupt that data or maliciously interfere with its operation. That's where memory protection comes in. By isolating the address space of each process, we prevent one from meddling with the memory of another, safeguarding the integrity of our system's operations. Now, you're probably wondering, how does the system keep track of all these separate address spaces? And that's where we introduce the concept of address translation. In protected mode, the x86 processor doesn't work alone. It's backed by a handy little component called the Memory Management Unit, or MMU for short. So what does the MMU do? Well, it's like the translator at an international conference. The programs on your system, they speak in terms of virtual addresses, locations in their own private address space. But the RAM, the physical memory of your system, it doesn't understand this virtual address lingo. It deals with physical addresses. The MMU acts as the interpreter between the two. It translates the virtual addresses used by the programs into the physical addresses in the RAM. This translation process allows each process to believe it has the entire memory to itself, while in reality, their data could be scattered all over the physical memory. It's like each process is living in its own virtual reality, oblivious to the actual layout of the physical world. So, what's the takeaway here? Protected mode does a fantastic job of isolating the memory spaces of different processes and translating their virtual addresses into physical ones, all thanks to the MMU. This forms the basis for a secure and efficient computing environment. And with memory protection in place, protected mode enables multitasking, but we'll save that for our next scene. Imagine running multiple processes concurrently without any interference. This is the magic of multitasking, a feature facilitated by protected mode. In the bustling world of computing, multitasking is akin to a skilled juggler keeping several balls in the air at once. Each ball, or in this case each process, runs independently of the others, yet simultaneously. How does this happen? Well, it's all about memory. Each process is assigned its own protected memory space. This memory isolation ensures that one process cannot meddle with the memory of another. It's like giving each process its own personal playground, where it can run, jump, and play without bumping into the other kids. But there's more to it than just memory isolation. Protected mode also introduces the concept of privilege levels, known as rings. Picture these rings as concentric circles of security within the processor. Ring 0 sits at the heart of these circles, wielding the most power. This innermost ring is typically reserved for the operating system kernel, the core of the OS that interacts directly with the hardware. As we move outwards, each ring has progressively fewer privileges. Higher numbered rings are less privileged, having more restrictions on the kinds of operations they can perform. This hierarchical structure helps maintain system stability and security. It's like a castle with its king safely guarded at the center and layers of defenses radiating outwards. In this way, protected mode ensures that less trusted software runs in higher numbered rings, limiting their access to the system's vital resources. This prevents any rogue process from wreaking havoc on the system. It's a bit like a bouncer at a club, deciding who gets in and who has to stay on the outside. So, from juggling multiple processes to maintaining a hierarchy of privileges, Protected mode plays a critical role in creating a secure and efficient computing environment. But how does protected mode manage these various segments of memory? Stay tuned to find out. Segmentation is key to managing the memory in protected mode. This is where the concept of dividing memory into smaller manageable chunks, known as segments, comes into play. Each segment has its own set of access rights, providing an additional layer of protection. This concept, while inherited from real mode, becomes far more flexible and granular under protected mode. Imagine a large library with countless books. Segmentation is like categorizing these books into different sections, making it easier to find and manage them. Similarly, in a computer system, segmentation helps in organizing and protecting memory, ensuring that each process can safely and efficiently access its required data without interfering with others. Now let's talk about another critical aspect of memory management in protected mode: page tables. Page tables are essentially the translators in the memory management unit. They translate virtual addresses used by the programs into physical addresses in the RAM. Think of it like using a GPS to navigate through a city. The GPS takes the destination you input, which can be an address or a point of interest, and translates it into a set of coordinates that it can understand and use to guide you. Similarly, a page table takes a virtual address, which is the address a program uses, and translates it into a physical address, which is the actual location in memory where the data is stored. Page tables also enable advanced features like demand paging, where pages or blocks of memory are only loaded when they're needed. This is akin to only opening the books you need in our library analogy, rather than opening every book at once. It's an efficient way of managing memory and ensures that resources are not wasted. All these features, the segmentation of memory and the use of page tables, are made possible thanks to the 32-bit addressing capability of protected mode. This allows access to a much larger address space than the 20-bit addressing used in real mode, enabling systems to utilize more than 1 megabyte of RAM. All these features are enabled by the 32-bit addressing capability of protected mode. 32-bit addressing is a significant upgrade over the 20-bit addressing used in real mode. By expanding the addressing capabilities, it allows systems to access a larger address space than before. Picture this. Instead of being confined to a mere 1 megabyte of RAM, the system can now utilize up to 4 gigabytes. That's a substantial increase, wouldn't you agree? Now let's shift gears to something called the task state segment, or TSS. In the realm of protected mode, the TSS plays a crucial role in storing information about the current state of a task or process. Imagine it as a meticulous record keeper, diligently noting register values, stack pointers, and segment selectors. This information is vital for context switching, enabling the processor to switch tasks smoothly and effectively. It's like having a personal assistant, keeping track of your every move and ensuring a flawless performance. Now let's look at how protected mode handles interrupts. Interrupts are crucial for system responsiveness. In the world of computing, interrupts are events that temporarily divert the flow of processing from one context to another. In protected mode, interrupt handling is enhanced, allowing for more efficient and flexible management of both hardware and software interrupts. This is a significant upgrade from real mode, where interrupt handling was less dynamic. Now, let's talk about operating system support. Modern operating systems like Windows and Linux leverage protected mode to provide a secure and efficient computing environment. This mode offers enhanced features such as memory protection, multitasking, and system stability. It acts as a shield, protecting system resources from unauthorized access or modification. This combination of improved interrupt handling and robust operating system support makes protected mode an essential part of the x86 architecture. It's not just about protection, it's about performance and reliability too. Finally, let's discuss the transition from real mode to protected mode. During booting, your computer starts in real mode before transitioning to protected mode. This transition is a crucial step in the boot process, bridging the gap between the processor's simpler real mode and the more advanced protected mode. It involves setting up necessary data structures like the Global Descriptor Table, or GDT, and the Interrupt Descriptor Table, also known as the IDT. These tables help manage memory and handle interrupts respectively, paving the way for the secure and efficient operation of your system. But technology doesn't stop at protected mode. With the continuous advancements in computing, x86 architecture has evolved into what's known as long mode. This includes both 32-bit and 64-bit modes, offering even more capabilities for modern computing. With protected mode, your computer achieves a secure and efficient computing environment, laying the foundation for modern operating systems. The evolution from real mode to protected mode and beyond exemplifies the dynamic and ever-improving nature of technology.